Now that we have the notation started, we'll add to the notation in this lecture, but also you'll see that the purpose for adding and having some of this notation now is that now that we have established a convenient notation, we can transform uh, properties into new axes. And in particular, we're going to take a just simply a force or displacement vector, which is kind of the very simplest thing that we can transform. And the coordinate axes themselves we'll also talk about in the following lecture. So we'll continue to develop some notation and we'll talk about how to transform into a new coordinate system in this lecture. So just adding to our notation, we still have our property P, and we've talked about the components, and obviously when we have components going along each axis, what's going to be very useful is to have understanding that the angle between P and the x-axis could be called theta 1, and the angle, let's say, between the p-axis and x2 could be called theta 2, and then the angle between x3 and p could be called theta 3. And once you do that, now you can see the components are easily related by expressions we all know about with vectors. Remember how if you know the angle between a vector and another vector, you can project it down very easily with the cosine. And so just writing that out, we could say, aha, P1, the vector in the x direction is going to be P, magnitude of P cosine theta 1. And sometimes it's written as L1, where L1 is clearly cosine theta 1. We call that direction cosine. So all of them together are called the direction cosines. And, the same thing's true for P2. And you probably remember from your um, vector algebra that also if you made P a unit vector, right, then of course the direction cosines are simply P1 equals L1, P2 equals L2, P3. And that's because uh, we've divided by the magnitude of P in order to make the, the P a unit vector. And so then, of course, they would just equal the direction cosines. Okay, that's very fine. So just another more detail as to when we talked about projecting, these into P1 and then into P2 and then into P3. Now we have a little more detail on how to do that, which is that the angle between the vectors is necessary. All right, let's take this one step further. Now let's say that I have that original set of axes that I wanted. But now I'm going to change things up. And let's say I rotate in the plane so that this guy goes in this direction and this guy goes uh, actually let's not assume rotation. That's kind of limiting it. Let's just say that I have uh, a new coordinate system, and it could be anything. Let's say I'm tilting back a little bit. So let's say that it's still Cartesian. Let's say, and I'm tilting back, and then let's say that doesn't have to be, by the way, it could be anything. It's transformation of any axes. Later on, when we have tensors and we're trying to talk about certain specific cases, you may have to keep Cartesian. But right now, these are just some other three axes. It doesn't really matter, right? So clearly, what you could do is you could say that, all right, I have a new coordinate system. Oops, I should have put primes on all these. I have the new coordinate system, and that therefore we're going to have new components. They can't be the same components as the other one because I've gone to a new set of axes. But I could have started with the other one, right? So everything else is going to be the same. I just need to figure out how they're related. So because of our linear thinking from before, we can assume then, for example, that the new, let's draw our little p over here just so you don't forget. Let's recall that we had some force or resulting property, doesn't matter, some other vector, remember that was out there called p, and so we had that resolved into x1, x2, and x3, and now we're saying, well, of course, it must be the case that p, I could have started with the other coordinate system and I can have three components, p1, p2, p3 as well. But the question is, how are they related to the originals? You could say, all right, well, p1 prime is obviously got to be related to the sum of components of p1 along x1 prime, right, plus components of p2 along x2 prime, etc., right? And so you start to realize, well, what we're really saying then is that p1 cosine of x1, the angle between x1 and x1 prime, plus p2 cosine x2, the angle between those axes, etc. So we have our directional cosines, our L's, if you will, that we introduced in the previous slide. And so really we're just talking about having the original P's being multiplied by the directional cosines that are relationships between the axes. Right, so that's one of them, right? That's one of them. That's one of them, right? So let's define Cij, a matrix of Cij to be cosine between xi prime and xj. So it relates the angles to all of the other angles, right? So now we could say p1 prime equals c 1, 1, C, 1, 2. Oops, sorry about that. Oops. Actually, all right. Um, let's clear this. So when I advance this and clear this, just remember that all we're doing is now looking at these are all the cosines. We've proven that basically all we're doing is taking P1, right, and we're projecting it, onto the new direction. P2, we're projecting that on the new direction, and P3, we're projecting that on the new direction, adding them all up to give P1 in that new direction, right, the x-axis. And so we just simplified by saying, look, let's take all these cosines and we'll put them into just a separate matrix, right? So let's do that in the next. So the Cij are the cosines of the angles between the new and the old, right? Axes, right? And I've started to write that out before it got kind of messy with pixelization. So again, these are nothing more than directional cosines between what it says. So this is the cosine between 1 in the new system and 1 in the old system. This is cosine between 1, x-axis and the y-axis in new and the old system, etc. So obviously if I'm going from one generic to another, I need all the components. But think about this. If I'm going from one Cartesian coordinate system to another Cartesian coordinate system, this thing's become super simplified usually, right? Because let's suppose I just rotate about the z-axis. Z stays the same. So the angle between the two x3s is 0, which means the cosine's 1. All the crosses are all 0. And then 1 and 2, that is the x and the y, just have simple rotation cosines about them. So some of these could be very simple or they could be very complex. If I just rotate, into any 3 space, then of course it gets complicated because I have to do all the angles. So just to finish this out, it looks like any other, and you can see why we do this kind of thing. When you see these symmetries, just by having this now powerful matrix and tensor notation stuff, we can easily transform everything in using the same notation. So we're still using the same notation to represent different things. Before we could say, well, I'm using the matrices to define, what the tensors are that relate, a force to a displacement. And here I'm using a matrix to define a new and an old coordinate system, and I'm using it specifically here to transform a force or displacement vector from one coordinate system to another. Remember, P1, P2, P3 is a force or displacement vector in the original coordinate system. And all I'm doing here is transforming that into the new coordinate system. And there you have it. And so, of course, now with our cute little shorthand notation, we can say that any of the components in the new coordinate system can be written as a directional cosine transformation matrice times that. And again, remember this implies the sum. That's why you've got the sum that you're seeing through here. So if I put a highlight around here to let you know, again, you notice how, and this confuses some students, the notations are all looking the same, but remember we're doing something very different here. Cij here are just directional cosines in here, right? And this is, you know, you can imagine as a force or displacement vector. And then this is the same one in new coordinate system. Right? So, not too much of a jump in this lecture. We just defined how you resolve P onto the axes. Remember, we did that in the two lectures ago. We had taken P and resolved into P1, P2, P3. Here we just formed, hey, there's cosine thetas between P and those directions. Those cosine thetas can be grouped into a matrix that allows us to transform a vector, and in our case, the vectors we care about are forces and displacements, right? We can transform them into another coordinate system. And again, just to remind you, and I'll talk about this in more detail later, transforming into different coordinate systems is important because you'll often get properties that are attached to some sort of crystal system that's been defined. So for example, in the cubic material, your elastic constant is going to be in reference to the principal axes being along the cube edges. But suppose that I am working in some material system where I always get slices of 111 material out of there. And so the normal to the 111 direction is where I'm measuring some properties, let's say, all the time, right? And so I need to transform let's say, some properties that are given in a tensor, or I'm measuring something in a vector that's coming out, and it's typically the elastic constants or whatever are given in the original system, and I need to transform them into the 111 direction because I work in there all the time, right? And so that's the kind of example, and we'll go through some more examples of that in the future. But right now, we simply, in this lecture, just covered how we can use the directional cosines in a transformation matrix to transform our old components into the new system.